Hello, I'm Chris Tice. I'm Vice President of Hardware Marketing and Manufacturing in the System Design Group of Synopsys. I'm happy to be here today, well, at least virtually, to actually talk to you about a keynote that I gave in 2017. So I'll be reprising my keynote from DVCon India 2017, where I addressed the Petacycle challenge. And then I'll talk about how this challenge has expanded in the more than more era, enabling software first as a critical element of success. Semiconductors continue to drive the world's electronics, particularly around artificial intelligence and cloud. Automotive has emerged as a critical segment in the world's electronics, as a convergence platform and as a platform for innovation. And as the world shifts particularly to autonomous driving and electric vehicles, this is a very critical segment. And I'll be talking about this in the second half of my presentation as we look toward expansion into a first software world. So following along on that automotive theme is that automobiles are shifting from standalone vehicles where the electronics are only concerned with the vehicle itself to a mesh connected environment where they're looking around themselves as well as connected out to the cloud. So today we have the connected car, and this is actually today, not even the future. The connected car has moved from standalone to a mesh-based environment. If you look at some of the components of this connected car, first, it's the environmental awareness, vehicle to vehicle, vehicle to the cloud. That's where you're getting your traffic information, you're communicating potentially to other vehicles, and actually even potentially in the future connecting in smart cities to the traffic signals themselves. Driving is a key aspect of electronics in cars today. Navigation, of course, which we've had for many years, moving to ADAS and other assisted systems. But now the dream has been to move to autonomy and full self-driving vehicles. And then you couple that with better safety, crash avoidance and pedestrian safety, seeing the world around you as part of the electronics in the car. And then, of course, we have to be entertained because we have more of the car being taken care of for us. So what are we going to do? So now we have infotainment, climate control, even perhaps massaging seats to make us relax when we get to our destination. And then you don't want to get overly relaxed, and so now there's driver awareness, sensing, alertness, and gestures all being built into the vehicles. But what powers this? It used to be that these were fairly rudimentary semiconductors, controllers in embedded control domains. Now, in today's vehicles, it's really a mobile connected supercomputer array that's driving the electronics inside a car. So it's not just about the connected car, it's also about pandemic-driven network traffic. When I talked to you in 2017, I talked about all the new port requirements, greater port density, faster speeds, and programming flexibility, software-defined networks for ASICs in network control, and all these new challenges around size and complexity and time to market. Well, the pandemic has really exacerbated these challenges. And now you have multiple streams running simultaneously. At the time I cited in an apartment complex, today this is maybe even your house. You might have one set of your family watching TV, maybe streaming Netflix, Prime Video, or Apple TV, while many of you are also working. Your children may be working from home as well, or going to school, I should say, not working, but going to school from home. And then you're perhaps on Teams or Zoom or Google Meet. The point of this is all of this streaming is all concentrated. It was just making the network traffic enormously overloaded. So then there's new designs. Just to give you an example of this design density is if you think about 30 minutes of ultra high definition streaming, it's about 64 gigabits. So 30 streams is about 2 petabytes, 2 petabits of bandwidth that's being consumed. And now that I used to say that was in a city, now it's actually coming out of your house perhaps. Now, that's just one example. I also talk about other areas of software cycles being driven, 5G and 5G applications, now moving even into 6G. And I talked back then about the gigabit packet rates on 5G and the verification challenge of symbol generation and testing of a 4K FFT as part of the 5G connectivity. 13 petacycles per iteration, so it's enormous, complex environments. I also talked earlier in this presentation about autonomous driving, escalating exponentially the need for computing inside vehicles. Sensing and perception, sensor fusion, planning what's going on as it senses in the environment, actuation, visualization, all of this autonomous driving, when you think about the computational load on the system in terms of double precision MIPS, it's upwards of three minutes of ADAS translates into 5 petacycles of calculation required to drive, from here down to the end of the street, perhaps. So again, these are huge computing needs, and the software required to validate that is enormous. And now I also talked about artificial intelligence, and in that case, it was artificial intelligence in the data center. But now, as things have evolved, as AI techniques are actually evolving to be edge-based systems and being a potential solution for the computational requirements inside automotive. But what underpins all of these application segments and the challenges in these segments is enormous amounts of cycles required to run realistic scenarios. And if you want to do the validation or verification of this, not only just from a silicon perspective, but also from a software perspective, it requires an enormously fast platform to accomplish this. That's the Petacycle challenge, and that's what I talked about in 2017. When I joined Synopsys in 2017, I was called the father of emulation because of my long history in emulation technology stretching back to 1991. Well, let me give you a recap of my talk of 2017 and talk about some of the predictions that I had made back then. Back then, I reviewed the evolution of emulation technology as it started with small commercial-based FPGA systems, eventually evolving into custom-based FPGA systems, and then custom processor-based systems. Each of these systems had their limitations of capability, long development time, capacity, and also performance, and then eventually massive power. You would get, every generation would have minimal capacity increases, and actually even less so from a performance perspective. Performance almost was locked into the 1 to 2 megahertz range. It was like a performance wall. With the advent of modern commercial FPGA-based solutions in the mid-2000s to late 2010s, is that what we saw is commercial FPGA-based emulation systems based on stacked silicon die and gigabit interconnect really solved the challenges of interconnect and density of the original emulation systems. And that, when coupled with the software stack, and a full software stack, enabled a fully functioning, fully capable emulation system. Emulation is a very difficult technology to develop. It takes great vision and stamina to realize these supercomputer class platforms with full OS and application software stacks. I appreciate the vision and dedication of the Synopsys team in the short time that I've been here that has realized 4 generations of systems in 5 short years, driving the solutions that enable the fast emulation that is required by these Petacycle challenges. Fast emulation is really what's required, and what solves that is the latest technology, ZeBu EP1. ZeBu EP1 is a 10 megahertz emulation system with up to 2 billion gates of performance. It's a staggeringly capable machine. And this is all in a single platform, which the alternatives take up to 2 platforms to deliver, and frankly don't even deliver all of the capability. The capability of this system provides for at-speed, full visibility debug, and it supports all the emulation use cases. But most importantly, because of its performance, it's the first trillion cycle emulator. That trillion cycle emulator enables you to actually run up to 15 minutes of real time in a practical sense. Remember, I talked about in the beginning this Petacycle challenges. This is the fast emulation platform required to help solve those Petacycle challenges. It's fast enough to actually allow you to practically run Antutu for mobile device characterization. And in these emerging automotive segments, be able to run, OnStar or even Alexa in your car. Can you imagine, those of you that like me that have Alexa at home and you shout at it sometimes trying to get it to turn on your lights? Can you imagine now that you're evolving from shouting at your car to shouting at your emulator, please turn on the lights? But the point of this is that this trillion cycle capability and almost and the ability to run real time enables us to provide solutions for not only shift left verification, but the software first era. And the software first era means that you're using software to drive system-level platforms, and system-level development. So let's take a look at companies that are embracing the software first as a lead design paradigm, including those that are using vertical integration of hardware and software and their winning strategies. Tesla, for example, in their latest earnings release, talked about the fact that their semiconductor and firmware teams are designing upwards of 19 variants of platforms, all software enabled, so that they can react to semiconductor shortages in this global supply chain environment. This capability, this flexibility that allows them to overcome supply chain interruptions was admired by Herbert Diess, the chairman of VW. He talked about how that the flexibility, the agility of Tesla is something to admire, and that within 2 to 3 weeks they had new software which allowed them to use different chips. As a matter of fact, what we also understand is he invited Elon Musk to come speak to VW. We look at Apple. Apple is a shining example of vertical integration with a software-first mentality, leveraging, for example, their M1 chip, originally designed for iPhones. It created a fully optimized architecture that really just outshines prior iterations. They were based on off-the-shelf silicon, and now it's expanded into the iPad and now into the desktop systems. And it's a showcase of hardware-software co-design. And then, of course, a very simple quote from Pat Gelsinger. Pat says, if you're delivering software that isn't, or delivering silicon that isn't supported by software, it's a bug. And that brings to mind something that I used to say a few years ago, which is the world is changing. It used to be it's all about first silicon, but now it's about first software. Because first silicon, as Pat said, without software is dead. It's just a piece of sand. You need the software to make the chip work. There are other companies that are adopting this software-first approach. We talked about Intel using what they call software-first. We look at Sci-Fi, and Sci-Fi using software-first for its AI-enabled designs. And this is a really critical point that I'll talk about in a moment. The combination of the AI software plus the underlying AI architecture really forms a closed-loop system that you need to optimize. And you can optimize from a power, performance, and area perspective. And it's very, very critical in automotive applications. Toyota talked about moving its development methodology to a software-first approach that undertakes this product development paradigm before they start, which is very much different from before. And finally, Renesas, as a supplier to companies like Toyota, also has to embrace the software first, because that's really what they're delivering, is the software on top of their semiconductors. So let's take a look at major automotive companies and as they adopt this hardware, software, vertical integration, and software-first approach. So this is a slide from Bertolt Hellenthal, who's the GM of electronics for Audi. And in this slide, what he talked about was, and he compared, was the automotive electronic design process compared to semiconductor. So on the left side was an advanced semiconductor design development paradigm about virtual development process, hardware, software co-design, virtual prototyping, and extensive use of simulation. Compared that to automotive, where he talked about it as a linear, non-virtual development process with no virtual prototypes. Semiconductor design times are, can be less than 18 months, less than a year, sometimes even less than 9 months, versus 5 to 7 years in the automotive space. And he talked about wanting to transform Audi's development methodology to a virtual development process, embracing hardware, software co-design, virtual prototyping, and ECU simulation models. And that actually has been used extensively in some of the latest generation Audi cars. As a matter of fact, I'm driving one of them that I saw on that plant. Another trend, similarly, is GM moving their entire environment. This is from Mary Barra, the CEO of GM, in her 2018 November investor call. And what she talked about was the transformation of GM development, because they're moving away aggressively from internal combustion engine technology to electric vehicle technology. And they can't afford to spend the 50 years that it took to perfect it before. They were trying to accomplish this over the next 5 to 7 years. And one of the ways to do that was to reduce development costs using virtual tools, virtualization to increase their time to market. And how do they do that? It's shift left from a verification and validation, and it's also about software first, and it's also about massive system virtualization. So it's not just virtualization of the SoC, and it's not just virtualization of an ECU, it's systems of systems virtualization. So it's systems of ECUs now all running together. And these are active programs in the next generation of GM's electric vehicle environments. So what this means from the automotive perspective, as an example of shift left in software or software first environments, is the following. So if you think about what we have from a classic semiconductor design, we have a fairly well-formed design and verification platform around this notion of a verification continuum. Various companies call it different things. Synopsys, we call it the verification continuum, which allows you to define, execute, and implement SoC from its abstraction and architecture level all the way through to the implementation level across the different engines of that. But the critical thing is that the continuum allows you to shift left the verification, basically pulling late-stage bugs post-silicon into pre-silicon and actually early on into the design process so that you can actually create a zero-defect approach. And so that's another key concept of software first, is that you attack and go after zero defects using advanced platforms, emulation, and prototyping technologies. The second then is to take that platform and abstract it into a virtual platform for the SoC. And so this virtualization then allows you to do tuning of the software, bringing up of the software in the first place, tune the architecture while you're still early on in the development cycle, and allow you to optimize the software and hardware simultaneously. The third shift left is actually to take that virtual SoC, it has virtual components inside it, and actually create an entire virtual ECU. And that virtual ECU is actually a system of SoCs, many of these inside the same system, and then actually run these against the real environments, the true EE system design and verification, where you have models and multi-physics models of the entire environment. That allows you to create accurate environments for your software, calibration, critical parameter optimization as well. Now, that's all about the shifting left. Then what you need, though, is that same environment to become persistent so that you can continuously refine, integrate, and verify this. So there's a persistence to this environment that then allows you to then implement and do over-the-air updates. Well, in order to do that properly, you need to be able to validate on an accurate platform the system and the software, and frankly, even the design that you may update over the air. And that's where you incorporate emulation and fast emulation capabilities. Tesla is a shining example of being able to do over-the-air updates. So let's dive deeper into this shifting left. And so what we want to do is shift left this entire error curve for earlier and higher productivity and cost. There is the notion that you want to really modernize what used to be a traditional development process. If you look on the left side of this diagram, you have the software developers generating code, creating application software, running on top, and this is connected to an automotive application, so running across the OS and the MCAL, the microcontroller abstraction layer, and then assembling that to build a full target software for a target CPU, and eventually you're in the engine control unit running the software binary, and then usually a couple of years after you get started, there's an actual ECU that you can run, and you can test this, and this is the classic hardware-in-the-loop testing. And hardware-in-the-loop is an automotive term, but it actually describes how we would do electronics, frankly, in the beginning as well, is that we often integrated software late stage in the process. And even when we developed newer technologies and newer platform technologies, is that oftentimes most of the software stack was done late in the process, after you actually had the system itself. This idea that you could actually abstract pieces of the system was one thing. We've evolved from pieces of the system to full SoCs to now full systems to now systems of systems. So now we can move to actual being able to use abstraction techniques where it's actually the software itself drives a system abstraction that enables you to run software in an accurate way, connect to test environments as well as environmental stimuli. And one example is the silver technology from Synopsys, which allows you to start to run what's called software in the loop. So now what you have is a software version of the platform, and you're actually iterating on that software platform view with your actual running platform itself. Then you can extend that using virtual development kits based on virtual prototyping technology, which give you a SoC up representation of the platform in conjunction with the software view. And then this gives you the ability to run against accurate platforms on a virtual hardware in the loop level of testing. Now that can be extended actually to the final integrated binary for automated regression testing. And then the result of that is a dramatic shift in the error curve, where instead of having all of this integration come at the very last stage of an integration program, now it shifts it way left. So now you see how this whole notion of the triple shift left fits together. So it's all about being able to create very early in the process the ability to create an abstraction of the platforms, and then be able to scale that abstraction to the population of software developers as well as system developers within your community. Extending beyond just an automotive-centric example, this whole idea of using this abstraction method for early OS boot and early software development extends to many cases. So, for example, Samsung used it extensively across their mobile application processor development. If you look at the left side is a slide that they had at DVCon in 2018 talking about their design process, moving from virtualizer to hybrid and emulation, and then shifting their tape-out dates inward because of the notion of virtualization. Look at the performance that you get out of these hybrid platforms and virtual prototyping platforms. A Linux boot moving from over 100,000 minutes to 1 minute. That's something that's productive enough for you to get your job done and actually to optimize and get software out the door as fast as possible. Inflame is another opportunity, another company out of China that's actually doing what I talked about, from a AI perspective, which is doing optimization of an AI network in conjunction with the software that runs on top of it by using a virtual prototyping abstraction of their AI architecture. And that allowed them to save 5 months in their architecture optimization and software as part of their release. Remember I said I'd get back to AI, particularly as we think about AI in an automotive context. So, we talked about, automotive being a convergence platform for electronics, as well as an innovation platform for electronics. As we look to this dream of full self-driving, and full autonomy, we talk about, and I said it was a supercomputer array of technologies. Well, the original autonomous vehicles had many, many computers in the trunk, sometimes affectionately called the junk in the trunk. Through application and integration, is that now that shrunk to parallel cores on one board, so the junk in the trunk shifted to a board, and then enabled by Moore's law is that we've been able to shift this to a chip and actually a redundant design inside the chip itself. So Moore's law enabled scaling. It basically takes that junk in the trunk and gets it to a chip. But you still have to develop the software that goes on top of it. And that's where you need these fast emulation platforms with their virtual representations. But there's more than that as well. In today's era, we have the more than more, or SysMore enabled scaling. So this is actually exploiting 3D IC packaging so that system makers are now scaling with 3D IC chips. And there's two components to this 3D IC scaling. One is integration, where you're actually bringing in different types of devices and interfaces, for example, optical in one case, or perhaps analog for PHY or PHY connecting, or even part of the plant control from an automotive perspective, as well as a disaggregation where you're actually taking some of the complex computational structures and changing from a traditional von Neumann implementation to AI-enabled architectures simultaneously with standard off-the-shelf computational capabilities in a chiplet type of model. Now, when you take all of this technologies, you've got all of these different interfaces and connectivity media connected with this chiplet technology, then you pack it into a three-dimensional array, you have an additional level of complexity, because now is that not only do you have systemic complexity, but you also have systemic implementation complexity. Because now you have to think in 3 dimensions from a power, area, and thermal perspective. And as you stack things up, is that you actually have to think about how does the power in one portion of the device or the system affect the power in another portion of the device or system. So power optimization, particularly in the context of software, because software activity will then drive activity within this whole 3D IC package. So in automotive SoCs, and particularly those that are AI enabled, it's about balancing power and performance. It's about meeting today's power requirements and budgets, but being able to scale with the maturation of the software as it gets smarter and smarter up to 5 years from now. You think about, and this is a graph that shows, and it's thanks to wave computing, inference per second as well as across the different power. And think about where we are with autonomous driving, is that we're looking at 3,000 to 5,000 inferences per second, which is an enormously complex device, moving up to 10 times that, to almost 100K inferences per second. So you have to then be able to optimize that environment against the power envelope as well as the thermal envelope, while actually maintaining and operating within your power budget for your battery technology. And it's all about battery technology and how long you can last in an electric vehicle. To help resolve the challenge of this is that we now have moved beyond, not only do we have fast emulation platforms, now we have application-specific platforms. And ZeBu M-Power is an example of that. So this is not only the fastest power emulator for software first, but it's also the fastest power emulator for hardware-software power validation. What the ZeBu M-Power is able to do is actually internal to the system, run all of the power calculations in the presence of a realistic software workload. And you can then run a power scan across the entirety of the software workload. So what that enables you to do is to be able to run large designs with realistic workloads, multiple iterations per day. And then the benefit of this is that you get actionable power profile for dynamic and leakage power, and then you have power critical blocks and vectors feeding into sign-off and thermal analysis. Remember I talked about in that 3D IC is that thermal is a critical aspect of that. Well, then taking this hardware and software architect for compute throughput and then applying that to the SoC-driven power analysis process, you have a continuum of the ability to optimize architecture, where you're doing that at the architectural level in these virtual workloads, where you're abstracting the software workloads, running power estimations, optimizing your platform. This is where you can make factors of performance difference when your architecture and your software comes together. Then moving into the RTL representation, and that's where the M-Power technology comes to bear, running target software against SoC RTL, and that is allowing you to run power profiles and optimize the power in specific areas of the devices or the chiplets, and then feeding that into cycle-based power, where you're looking at peak windows and then generating sign-off windows that you're doing the accurate sign-off for the final sign-off for power. So when you add thermal to this equation, then you've got a closed-loop validation for your dynamic voltage and frequency scaling. But thermal adds a whole new complexity to the problem. Thermal latencies are quite long, and so you have to run very many power profiles, 100 million cycle power profiles, and you need maybe 10 to 100 of those because the latency of the heating is slow in a relative basis. So you want to create many power profiles that then translate into multiple thermal profiles, and these thermal profiles represent terabytes of data. And that's where a ZeBu M-Power profiling engine allows you to do things like cycle-based or skip-level characterization. You're able to run fast out to specific points and then run a frame capture, then run fast again as a frame capture, matching the thermal latency of what you're trying to measure. That then creates the opportunity to integrate sensor technology and then do active power management with the power management firmware. So the benefit of this is that you're running power profiles from billions of cycles, and you're running thermal profiles every 50 to 100 milliseconds across these 100 and 200 million cycle runs. What you can then accomplish is the ability to have both accurate power and a thermal profile of this whole 3D IC package. And that's really is the key goal. So just to pull it all together, addressing the Petacycle challenge in this SysMore era. Remember, SysMore is the more than more scaling in 3D ICs. The first thing we talked about was the enablement of these fast emulation platforms and the shift-left methodologies to go after and create zero defect implementations. The second thing we talked about was using those fast platforms as ability to then validate real-time, real and actionable minutes of execution up to 15 minutes for 1 trillion cycles. Then you add that with power thermal from a 3D packaging perspective as a critical component to solving these problems. Now, one thing we didn't talk about is the importance of security and all the different security methodologies that have to be inculcated into today's design flow. As an engineer at Tesla said at one time, piece of insecure silicon is unsafe silicon, but that's a whole different chapter and we've run out of time for today. But the integration of all these factors together is all about system design success. And one of the goals of that, frankly, is to be able to be taken safely from one location to another in a very comfortable way. And as this example shows, you want to be taken safely from one location to another, be able to relax and enjoy and do some reading and catch up on your reading. And you may even want to read a book instead of an iPad. So I want to say thank you. Thank you for allowing me to come back and revisit some of these challenges. Thank you for spending the time with me today, and thank you to the DVCon organizing committee for inviting me to come back. Take care, stay healthy, and be safe.